Welcome everyone to EA Global Summit 2021. This is Juhi from EA Global Summit organizing team. Firstly, thanks to everyone for your interest and for joining us for this session. This session is by Stephen Hall, Senior Software Engineer from Spark Systems Australia, presenting this session about math solvers and SysFIS simulation in EA 15.2. Kindly note that we will be muting all the participants throughout the session, and if any one of you are having any questions during and after the session, please use the chat window to drop your questions to the speaker. We will be reading out the questions and the speaker will answer during the Q&A session at the end of this session. So, to enable collaboration and communication with Stephen and other EA practitioners after the session, we request you to visit the dedicated channel for this session in Microsoft Teams. Stephen and several other speakers have kindly accepted to stay in the channel to have a one-to-one discussion and answer your questions. The link to the Microsoft Teams channel is posted in the chat window for your quick reference. If anyone is having any difficulty in connecting to Teams, please reach us in the chat window or write to us at registrations@eaglobalsummit.com. Thanks once again for your interest and looking forward to the wonderful session with Stephen. Over to you, Stephen, now.
Thanks, Julie.
Yeah, I'll make you.
Hello, everyone. My name is Stephen Hall, and today I'll be giving an introductory overview of two of the new maths and simulation features available in the latest Enterprise Architect 15.2. The first new feature is the ability to call and run MATLAB functions directly from Enterprise Architect from anywhere that JavaScript can be run using the new Solver class. You can also call and run Octave functions, which is an open source alternative to MATLAB, but we'll focus on MATLAB today. The second new feature is the new OMG standard for SysFIS to construct SysML models for simulation in third-party programs such as MATLAB Simulink. SysFIS stands for SysML Physical Interaction and Signal Flow Simulation, and it standardizes a common way to specify variables and constants, types, and inputs and outputs for use in third-party simulations. It currently includes support for both the Modelica standard and for MATLAB Simulink. So let's start with the new solver classes in JavaScript. JavaScript can be used in many places inside Enterprise Architect, including state machine simulations, activity diagrams, BPMN simulations, inside custom plugins, or as raw scripts to be run on command. To call a MATLAB or Octave function, we have a new class called a solver. You can instantiate a solver class at the start of a script or in the initialization of a state machine or other simulation. The solver can then be used throughout the script or simulation to call MATLAB functions or to get or set variables in the MATLAB workspace. Here we see an example of a plain script invoking a new MATLAB solver and calling a native function using the exec command. The output of the function is stored in the MATLAB workspace and can be pulled back into JavaScript with a call to get the variable. As well as running complex maths functions to return the answer to JavaScript in Enterprise Architect, you can also tell MATLAB to run a chart, pop up a custom-built dialog, or run custom functions and routines. Any command that can be run from MATLAB's internal command line can be run by the solver class. Variables can be passed as either simple types, such as integers or floating point numbers, or character strings or arrays. They will be automatically converted into the appropriate MATLAB types when set, and converted back to the corresponding JavaScript type when retrieved back from MATLAB. While we wait for MATLAB to start in the background, I'll tell you a bit about what this script is doing. It's a random number generator, so after starting MATLAB, the solver makes a call to MATLAB to shuffle the random number generator. Next, it sets the variables needed for how the random numbers are to be distributed, and then another call to generate the array of random numbers. The MATLAB array of numbers is brought back into Enterprise Architect with a get call. And the final step is to run a verification calculation of the randomness of the generated numbers, followed by showing a plot of the distribution. And here's the output plotted in MATLAB. Here we see an example of an activity diagram that uses MATLAB to generate a complex output plot during different stages of the activity. The solver is created in the first step and can be used in subsequent steps of the activity. When the simulation is run, we see in the output that Enterprise Architect has launched MATLAB in the background and will run through the commands in each action and show the resulting MATLAB generated plot as the final stage. Here we see the plot popped up in a MATLAB window. We can also see the output from the various stages in the simulation output here. This second example shows a solver being used in a state machine that generates an estimate of the amount of power a solar panel can generate throughout the year. The maths for this equation is complex and relies on the latitude and longitude of where the panel is located. You can see that the solver code is used in a few different places throughout the state machine. The initialization is performed as an effect on the first transition, and more calculations are performed on the transitions here. If we look at the code for the plot the day function, we see a larger section of JavaScript for setting up a nice plot of the solar panel power during a 24-hour period. Again, using similar commands to execute MATLAB functions. While running the state machine simulation, you are not able to directly view the MATLAB internal workspace variables, but any that have been pulled in with the get command are visible in the local variables tab or can be outputted to the log window. Here we see the state machine looping through hour by hour and running a MATLAB calculation to determine if there will be enough solar output to run the machine. If the result from MATLAB is high enough, then it will step into the run machine state. Otherwise, it will transition to the idle state. And again, we see the output of the various stages in the output window. Another course for the state machine is to run MATLAB calculations for the total radiation for each day of the year. The result is then plotted. All the features of the MATLAB solver class are available for use with Octave as well, which has an almost identical feature set. The features we use were introduced to MATLAB in the R 2017B release and have been fully tested with the 2019 and 2020 releases. Next, we'll move on to looking at the new SysFIS standard from OMG and how it can help visualize and model your simulations. As I said earlier, SysFIS stands for SysML Physical Interaction and Signal Flow Simulation. This means it's an extension to SysML and as such can be used in SysML models in Enterprise Architect. There are two main types of systems that can be modeled with SysFIS. The first is signal flow, in which an element can send a signal or message to another element. That element can then manipulate the message and combine it with other signals and then pass on a new signal to the next block in the model. This is a more abstract style of modeling and matches up with the core Simulink features. The second type of system that can be modeled is a physical system, in which elements represent real-world objects and the connections between them represent real-world physical flow of a substance or energy. We will look at an example of this, where the elements are physical tanks to hold water and the equations define how the water will flow from one tank to the other based on variables such as pressure, height of the water, temperature, and viscosity. Previous versions of Enterprise Architect had some of the features of SysFIS available for use with the Modelica simulation library. The new version improves on that base by adding support for simulating using MATLAB Simulink application and allowing more detail about variables and ports to be seen on the diagrams themselves, allowing the model to self-describe its interactions rather than having to configure them in a special simulation window. For example, variables can be set to either constant or variable by setting a new SysFIS stereotype, and this will show up on the element under a new set of compartments. We've got FIS variables, FIS constants. The initial values can also be set in the properties page and seen on the diagram. And updated as they're changed. You can also define and see the type of the variable and the units it's measured in. In this case, because it's signal flow, the signal is just a number, so no units are used. Before we get started on these examples, it's necessary to import the SysFIS pattern libraries into your model. This defines some base types needed for signal flow and some base physical unit types for physical simulation. The SysFIS library can be imported via the model wizard. Look in the SysML perspective or search for SysFIS. The library should be imported once for each repository and then linked into each SysFIS model that uses it. It can be linked in using the package import connector. So let's look at an example of a SysFIS model using signal flow and how it can be modeled in Enterprise Architect and simulated in Simulink. Here we see an electronic signal processor composed of various filters and amplifiers. The block definition diagram, or BDD, shows that the electronic components are all derived from a base 2-pin component that has an input signal and an output signal. The ports are typed using the new SysFIS types that we just imported and are named as per the SysFIS specification. Sorry. If we look at the high pass filter, we see it has one PHS variable and one PHS constant, giving a consistent visual indication of the variable types used. We can see the variables using the new stereotype in the properties page, SysFIS PHS variable. If we look at the internals of the high pass filter, we see a parametric diagram detailing the equations that govern the filter. For signal flow models, the equations have a single output on the left or a single derivative of an internal variable. The variables, constants, and ports are all bound to the constraint parameters using binding connectors. Looking at the main signal processor block now, if we look at its internal structure, we see an internal block definition diagram, or IBD, that shows the flow of signals between instances of the various blocks. The signal processor itself has an input and an output, allowing it to be connected to and used in larger models. The signal flows from the input through an amplifier, is split into a low pass and high pass filter. Then the signals are mixed back together and sent to the output. We see the initial values of the internal variables on the properties themselves, which would allow easy differentiation if, say, you had multiple high-pass filters with different values on the same diagram. The signal processor itself is connected up to a source and scope viewer to allow the simulation to be performed. The signal source provides an input signal to the processor, and the sink is just so that the output has somewhere to go. To run the simulation, use the SysML configuration artifact. You now have the option to choose either Simulink or Modelica from the drop-down in the toolbar. We'll stick with Simulink today. We see all the blocks defined in our model on the left and a list of output properties that can be plotted in Simulink on the right. The options available to plot vary slightly between Modelica and Simulink, with Simulink's limited to output ports only. Generate and run the simulation by clicking Solve. MATLAB was starting and loading in the background as soon as I opened this tab, but now it also needs to load Simulink, which can take a few seconds. While it's loading, we can see in the system output that MATLAB has started in the background, and any warnings or errors that occurred while generating the simulation will appear here too. When finished, this will open MATLAB Simulink and show the output of the selected variables. And here's Simulink's graph of the output. To quickly see the effect of changing initial conditions, you can create a new data set in the simulation configuration screen. Here we have defined a new initial value for the amplifier to provide more amplification to the signal. Selecting the new data set and rerunning the simulation will show the larger signal. Note that the scale on the plots is different, with this one twice as large as the other. The input signal is unchanged, but all the other signals are increased due to the increased amplification in the first stage of the signal processor. Next, we'll look at a physical interaction model. This represents the physical flow of water from one tank to another via a pipe. To run this in Simulink, you need the Simscape extension that allows for physical modeling of systems. The difference with Simscape is that a connection between two blocks represents a physical connection between the components and allows for bidirectional flow of a substance or energy between the two components based on balancing the equations of each block. Here we see our block definition diagram showing the blocks for the tank reservoir and the connecting pipe. We see some variables and constants as well as some default initial values and real-world physical units. In contrast to the signal flow model, which had ports typed by real numbers with the direction the signal would flow, the physical model ports are typed by flow elements. These are defined in the SysFis library that was imported earlier. The volume flow element contains a single flow property typed by an in-out flowing volume block. This block contains two PHS variables for pressure and flow rate. For physical systems, there must be one conserved and one non-conserved variable. In Simulink, these are referred to as the through and across variables. This can be set on the properties page under the new SysFis variables properties. And is now visible on the diagram elements, making it clear what each variable's function is. The volume flow rate is conserved, meaning that the value of the flow rate will be equal and opposite to the other end of whatever it is connected to. That is to say, whatever flows out of the tank must flow into the pipe, and vice versa. The pressure variable is not conserved, meaning the pressure on one side of the opening is the same as the pressure on the other. In reality, this point represents the same physical location, so the pressures must be the same. The internal structure of the tank is a parametric diagram. It contains some equations governing how water will flow into or out of the opening based on pressure and other variables. We can see the constants and variables used in the equations, as well as the port variables controlling the flow of water into and out of the tank. Again, we see the internal variables, constants, and ports are bound to the constraint parameters using binding connectors. Next, we see the internal block diagram showing how the components are connected together. We see the first tank connecting to a pipe, which connects to a second tank. The initial height of the water in the two tanks is different, which will cause a pressure difference, which will cause the water to flow between the tanks through the pipe until the pressure is equalized. To run the simulation, we again double-click on the simulation artifact and set up the simulation to run in either OpenModelica or Simulink. We'll run this first with the default dataset, where the initial values are taken from the properties of the elements themselves, as seen on the various diagrams. This is SimScape's output plot window, which allows you to select the variables associated with the components that were selected to be plotted in Enterprise Architect. We see the heights of the water of the two tanks starts with tank 1 higher than tank 2. And as the water flows from the more full tank into the other, the height equalizes as the pressure equalizes, settling on a final value where the physical system is in equilibrium. Next, we'll run with a different data set, which will override any default initial values on the elements or blocks and use the values specified here. You can see that if we specify a larger diameter pipe, then the water pressure and fluid levels stabilize much faster than with the narrower pipe, because more water can flow through the larger pipe. Lastly, we'll see what happens if the two tanks are different sizes. The size is defined by the cross-sectional area of the tank. The list here shows any variables or constants that have been overridden in this dataset, making it clear that only the two tank sizes have been changed. Opening up the dataset, we get to the dataset configuration window, which shows a list of the default values set on the blocks, or from the initial values set on a property. Tank 1 then has its surface area overridden from 4 meters squared to 8, while tank 2 has been reduced in size to 2 meters squared. When we compare the output plots, it is clear that the height of the water in the larger tank reduces more slowly than the small tank, and the pressure equalizes with a different height than before. In a real-world scenario, this could indicate a problem. For example, if the smaller tank isn't tall enough to handle the 35 meters height of water indicated in the simulation output. State machines in Enterprise Architect can be used to control the flow of a SysFIS simulation. These state machines can also be exported to Simulink using another extension called Stateflow that adds state machine control to Simulink diagrams. We see in this example a signal flow model of a humidifier system. To simulate the user interaction and control the on-off state of the machine, there are a handful of SysML state machines. When we simulate this with Simulink, you can see that state flow diagrams are created to match what was in Enterprise Architect. Move that down a bit. Once simulating in Simulink, you are able to debug the state machines and step through them at different speeds while inspecting the variables. These state machines are useful for cases where the equations are non-linear and depend on the state of the system to pick which equations to use. In this case, the equations for when the humidifier is on versus when it is off are different and mostly independent, so controlling via a state machine makes sense in this situation. Enterprise Architect includes a few patterns that reference common blocks that exist in both Simulink and Modelica. These common blocks are those that are defined by the SysFIS standard. You can access them via the patterns icon in the SysFIS toolbox. It's also possible to reference other already existing blocks, including custom blocks that you've written yourself, by specifying the name of the library block and its inputs and outputs. Here we can see model blocks that reference a resistor, op-amp, and other electrical components to model an inverting op-amp using components that exist in Simulink. I'm going to drop a capacitor block here from the electrical components package section. You can see it automatically adds the required constants and ports for both Simulink and Modelica. The block itself is typed by two new stereotypes, Simulink block and Modelica block, which indicate that this is a reference to an existing component in both programs. The new stereotypes have an associated property that specifies the name of the block in Simulink or Modelica. We see that the capacitor has a path in Simulink under the Foundation Electrical Elements library and a similar path in Modelica. The constants and variables are likewise typed by new SysFIS stereotypes, Simulink parameter and Modelica parameter. These two have associated properties for the name and value to be used in the simulation program. Here we see the Simulink parameter called C and is given a default value of 0, which will be overridden in the model later. The Modelica name is similar, but is a capital C. If we open up the generated model in Simulink, which I don't have open, let me open that very quickly for you. I can see that instead of plain square blocks, we have references to proper Simulink and Simscape blocks from their library. This also demonstrates a crossover between the signal flow domain and the physical domain. The initial input is controlled by a sine wave signal, which is converted to the physical domain so that it can control the voltage source. Simscape shows the physical domain connectors using different colors for different physical domains, whereas Simulink signals are shown as black lines with arrowheads to indicate the direction of signal flow. Another thing you may want to do is have a high-level model inside Enterprise Architect, but the detailed mathematical view of the model kept inside Modelica or Simulink. This is possible too. Enterprise Architect will generate the outline of the model in Simulink for you and allow the details to be filled in later in Simulink. Conversely, you may already have detailed blocks well defined inside Simulink, in which case you are able to reference those blocks from within EA to incorporate them into the larger model. Here we can see a high-level model of a system within Enterprise Architect. The blocks are defined and the IBD shows how the parts are connected together. But there are no constraint equations governing the block's behavior and no other internal structure defined except for the input and output ports. After running the simulation, you will end up with Simulink files that show the block structure and connections but have no internal structure. Here's a top-level model. We see the high-level structure as defined in Enterprise Architect. If we go into the internals, we again see the connectors between the components connecting up into the ports. If we go into the internals of one of the components, however, we see that there is no internal structure ready for someone else to fill in the mathematical details of the component. Once the outline structure is generated for Simulink, it won't be generated again each time, so changes made inside Simulink will remain. And that concludes this introductory overview of two of the new maths and simulation features available in the latest Enterprise Architect 15.2. We looked at using the new solver class in JavaScript to call MATLAB or Octave functions, and how to create and use the new SysFIS standard for SysML to simulate your models in third-party applications such as MATLAB, Simulink, and OpenModelica. I'll pass back to Jeannie now to go over any questions posted during the presentation. Thank you.
Yeah, thank you, Steve. So I'm just looking for some questions. So far, we haven't received any questions. Okay. So thanks, Steve, and thanks to everyone for your time during the session. Now, Steven will be available in MS Teams to have detailed discussion and answer more questions in Microsoft Teams. The link to Microsoft Teams is pasted in the chat window for your quick reference. If anyone is having any difficulty in connecting to Teams, please reach us at this chat window or write us at registrations@eaglobalsummit.com. Thanks once again, everyone, and looking forward to hosting you all in another wonderful session at this summit shortly. Thanks, Steve, once again.